Let us start with the second chapter of this course, testing through the software life cycle. Testing is not a standalone activity. It has its place within a software development life cycle model, and therefore the life cycle applied will largely determine how testing is organized. There are many different forms of testing. Because several disciplines, often with different interests, are involved in the development life cycle, it is important to clearly understand and define the various test levels and types. The organization of testing activity will largely depend on the SDLC model that is used for development of a software. So we will start our discussion with the discussion of some main SDLC models. To understand test organization, we have to first understand the different SDLC models. The development process adopted for a project will depend on the project aims and goals. There are numerous development life cycles that have been developed in order to achieve different required objectives. These life cycles range from lightweight and fast methodologies, where time to market is of the essence, through to fully controlled and documented methodologies, where quality and reliability are key drivers. Each of these methodologies has its place in modern software development, and the most appropriate development process should be applied to each project. The models specify the various stages of the process and the order in which they are carried out. The life cycle model that is adopted for a project will have a big impact on the testing that is carried out. Testing does not exist in isolation. Test activities are highly related to software development activities. It will define the what, where, and when of our planned testing, influence regression testing, and largely determine which test techniques to use. The way testing is organized must fit the development life cycle, or it will fail to deliver its benefit. If time to market is the key driver, then the testing must be fast and efficient. If a fully documented software development life cycle, with an audit trail of evidence, is required, the testing must be fully documented. In every development life cycle, a part of testing is focused on verification testing, and a part is focused on validation testing. Verification is concerned with evaluating a work product, component, or system to determine whether it meets the requirements set. In fact, verification focuses on the question, is the deliverable built according to the specification? Validation is concerned with evaluating a work product, component, or system to determine whether it meets the user needs and requirements. Validation focuses on the question, is the deliverable fit for purpose, e.g. does it provide a solution to the problem? The V model provides guidance that testing needs to begin as early as possible in the life cycle, which is one of the fundamental principles of structured testing. It also shows that testing is not only an execution-based activity. There are a variety of activities that need to be performed before the end of the coding phase. These activities should be carried out in parallel with development activities, and testers need to work with developers and business analysts so they can perform these activities and tasks and produce a set of test deliverables. The work products produced by the developers and business analysts during development are the basis of testing in one or more levels. The V model provides guidance that testing needs to begin as early as possible in the life cycle, which is one of the fundamental principles of structured testing. It also shows that testing is not only an execution-based activity. There are a variety of activities that need to be performed before the end of the coding phase. These activities should be carried out in parallel with development activities, and testers need to work with developers and business analysts so they can perform these activities and tasks and produce a set of test deliverables. The work products produced by the developers and business analysts during development are the basis of testing in one or more levels. By starting test design early, defects are often found in the test basis documents. A good practice is to have testers involved even earlier, during the review of the draft test basis documents. A good practice is to have testers involved even earlier, during the review of the draft test basis documents. The V model is a model that illustrates how testing activities, verification, and validation can be integrated into each phase of the life cycle. Within the V model, validation testing takes place especially during the early stages, e.g. reviewing the user requirements, and late in the life cycle, e.g. during user acceptance testing. Although variants of the V model exist, a common type of V model uses 4 test levels. The 4 test levels used, each with their own objectives, are 1. Component testing, searches for defects in and verifies the functioning of software components, e.g. modules, programs, objects, classes, etc., that are separately testable. 2. Integration testing, tests interfaces between components, interactions to different parts of a system such as an operating system, file system and hardware, or interfaces between systems. 3. System testing, concerned with the behavior of the whole system/product, as defined by the scope of a development project or product. The main focus of system testing is verification against specified requirements. 4. Acceptance testing, validation testing with respect to user needs, requirements, and business processes conducted to determine whether or not to accept the system. Not all life cycles are sequential. There are also iterative or incremental life cycles where, instead of one large development timeline, from beginning to end, we cycle through a number of smaller self-contained life cycle phases for the same project. As with the V model, there are many variants of iterative life cycles. A common feature of iterative approaches is that the delivery is divided into increments, or builds, with each increment adding new functionality. The initial increment will contain the infrastructure required to support the initial build functionality. The increment produced by an iteration may be tested at several levels as part of its development. Subsequent increments will need testing for the new functionality, regression testing of the existing functionality, and integration testing of both new and existing parts. Regression testing is increasingly important on all iterations after the first one. This means that more testing will be required at each subsequent delivery phase, which must be allowed for in the project plans. This life cycle can give early market presence with critical functionality, can be simpler to manage because the workload is divided into smaller pieces, and can reduce initial investment, although it may cost more in the long run. Also, early market presence will mean validation testing is carried out at each increment, thereby giving early feedback on the business value and fitness for use of the product. Examples of iterative or incremental development models are prototyping, rapid application development, RAD, rational unified process, RUP, and agile development. In summary, whichever life cycle model is being used, there are several characteristics of good testing. 1. For every development activity there is a corresponding testing activity. 2. Each test level has test objectives specific to that level. 3. The analysis and design of tests for a given test level should begin during the corresponding development activity. 4. Testers should be involved in reviewing documents as soon as drafts are available in the development cycle. Next, we will discuss various test levels. The first test level is component testing. Component testing, also known as unit, module, and program testing, searches for defects in and verifies the functioning of software, e.g. modules, programs, objects, classes, etc., that are separately testable. Component testing may be done in isolation from the rest of the system depending on the context of the development life cycle and the system. Most often, stubs and drivers are used to replace the missing software and simulate the interface between the software components in a simple manner. A stub is called from the software component to be tested. A driver calls a component to be tested. Component testing may include testing of functionality and specific non-functional characteristics such as resource behavior, e.g. memory leaks, performance or robustness testing, as well as structural testing, e.g. Decision coverage. Test cases are derived from work products such as the software design or the data model. Typically, component testing occurs with access to the code being tested and with the support of the development environment, such as a unit test framework or debugging tool, and in practice usually involves the programmer who wrote the code. Sometimes, depending on the applicable level of risk, component testing is carried out by a different programmer, thereby introducing independence. Defects are typically fixed as soon as they are found, without formally recording the incidents found. One approach in component testing, used in extreme programming (XP), is to prepare and automate test cases before coding. This is called a test-first approach or test-driven development. This approach is highly iterative and is based on cycles of developing test cases, then building and integrating small pieces of code and executing the component tests until they pass. After component testing comes the integration testing. Integration testing tests interfaces between components, interactions to different parts of a system such as an operating system, file system, and hardware, or interfaces between systems. Note that integration testing should be differentiated from other integration activities. Integration testing is often carried out by the integrator, but preferably by a specific integration tester or test team. There may be more than one level of integration testing, and it may be carried out on test objects of varying size. For example, component integration testing tests the interactions between software components and is done after component testing. System integration testing tests the interactions between different systems and may be done after system testing. In this case, the developing organization may control only one side of the interface, so changes may be destabilizing. Business processes implemented as workflows may involve a series of systems that can even run on different platforms. The greater the scope of integration, the more difficult it becomes to isolate failures to a specific interface, which may lead to an increased risk. This leads to varying approaches to integration testing. Integration testing is broadly categorized into two types. Big Bang approach. In this approach, all the different modules are integrated at the same time, and then all the interfaces are tested in one go. This does not require the development of stubs and drivers. The problem with this approach is that as the system grows in size, it becomes difficult to pinpoint or debug the reason for an issue or defect. So Big Bang integration may seem like a good idea when planning the project, being optimistic and expecting to find no problems. If one thinks integration testing will find defects, it is a good practice to consider whether time might be saved by breaking down the integration test process. The second approach to integration testing is the incremental approach. In this approach, the modules of a system are integrated one after another. We may take either of the below three approaches for this. 1. Top-down testing takes place from top to bottom, following the control flow or architectural structure, e.g. starting from the GUI or main menu. Components or systems are substituted by stubs. 2. Bottom-up testing takes place from the bottom of the control flow upwards. Components or systems are substituted by drivers. 3. Functional incremental integration and testing takes place on the basis of the functions or functionality as documented in the functional specification. The next test level is system testing. System testing is concerned with the behavior of the whole system/product as defined by the scope of a development project or product. It may include tests based on risks and/or requirement specification, business processes, use cases, or other high-level descriptions of system behavior, interactions with the operating system, and system resources. System testing is most often the final test on behalf of development to verify that the system to be delivered meets the specification, and its purpose may be to find as many defects as possible. Most often it is carried out by specialist testers that form a dedicated and sometimes independent test team within development, reporting to the development manager or project manager. In some organizations, system testing is carried out by a third-party team or by business analysts. Again, the required level of independence is based on the applicable risk level, and this will have a high influence on the way system testing is organized. System testing should investigate both functional and non-functional requirements of the system. Typical non-functional tests include performance and reliability. Testers may also need to deal with incomplete or undocumented requirements. System testing of functional requirements starts by using the most appropriate specification-based black box techniques for the aspect of the system to be tested. For example, a decision table may be created for combinations of effects described in business rules. Structure-based white box techniques may also be used to assess the thoroughness of testing elements such as menu dialog structure or web page navigation. System testing requires a controlled test environment with regard to, amongst other things, control of the software versions, testware, and the test data. A system test is executed by the development organization in a properly controlled environment. The test environment should correspond to the final target or production environment as much as possible in order to minimize the risk of environment-specific failures not being found by testing. The last test level that we will discuss is the acceptance testing. When the development organization has performed its system test and has corrected all or most defects, the system will be delivered to the user or customer for acceptance testing. The acceptance test should answer questions such as: can the system be released? What, if any, are the outstanding business risks? And has development met their obligations? Acceptance testing is most often the responsibility of the user or customer, although other stakeholders may be involved as well. The execution of the acceptance test requires a test environment that is, for most aspects, representative of the production environment, as if production. The goal of acceptance testing is to establish confidence in the system, part of the system, or specific non-functional characteristics, e.g. usability, of the system. Acceptance testing is most often focused on a validation type of testing, whereby we are trying to determine whether the system is fit for purpose. Finding defects should not be the main focus in acceptance testing. Although it assesses the system's readiness for deployment and use, it is not necessarily the final level of testing. For example, a large-scale system integration test may come after the acceptance of a system. Acceptance testing may occur at more than just a single level. For example, a commercial off-the-shelf COTS software product may be acceptance tested when it is installed or integrated. Acceptance testing of the usability of a component may be done during component testing. Acceptance testing of a new functional enhancement may come before system testing. Within the acceptance test for a business supporting system, two main test types can be distinguished as a result of their special character. They are usually prepared and executed separately. The user acceptance test focuses mainly on the functionality, thereby validating the fitness for use of the system by the business user, while the operational acceptance test, also called production acceptance test, validates whether the system meets the requirements for operation. The user acceptance test is performed by the users and application managers. In most organizations, system administration will perform the operational acceptance test shortly before the system is released. The operational acceptance test may include testing a backup/restore, disaster recovery, maintenance tasks, and periodic check of security vulnerabilities. Other types of acceptance testing that exist are contract acceptance testing and compliance acceptance testing. Contract acceptance testing is performed against a contract's acceptance criteria for producing custom-developed software. Acceptance should be formally defined when the contract is agreed. Compliance acceptance testing or regulation acceptance testing is performed against the regulations which must be adhered to, such as governmental, legal, or safety regulations. If the system has been developed for the mass market, e.g. commercial off-the-shelf software, COTS, then testing it for individual users or customers is not practical, or even possible in some cases. Feedback is needed from potential or existing users in their market before the software product is put out for sale commercially. Very often this type of system undergoes 2 stages of acceptance test. The first is called alpha testing. This test takes place at the developer's site. Alpha testing may also be carried out by an independent test team. Beta testing, or field testing, sends the system to a cross-section of users who install it and use it under real-world working conditions. The users send records of incidents with the system to the development organization, where the defects are repaired. Note that organizations may use other terms, such as factory acceptance testing and site acceptance testing for systems that are tested before and after being moved to a customer's site. The next topic we will be discussing is test types. Test types are introduced as a means of clearly defining the objective of a certain test level for a program or project. Focusing the testing on a specific test objective and, therefore, selecting the appropriate type of test helps making and communicating decisions against test objectives easier. A test type is focused on a particular test objective, which could be the testing of a function to be performed by the component or system, a non-functional quality characteristic such as reliability or usability, the structure or architecture of the component or system, or related to changes, i.e. confirming that defects have been fixed, confirmation testing, or retesting, and looking for unintended changes, regression testing. Depending on its objectives, testing will be organized differently. For example, component testing aimed at performance would be quite different to component testing aimed at achieving decision coverage. The first test type that we would discuss is functional testing. The function of a system, or component, is what it does. This is typically described in a requirement specification, a functional specification, or in use cases. There may be some functions that are assumed to be provided that is not documented that are also part of the requirement for a system, though it is difficult to test against undocumented and implicit requirements. Functional tests are based on these functions, described in documents, or understood by the testers, and may be performed at all test levels, e.g. Test for components may be based on a component specification. Functional testing considers the specified behavior and is often also referred to as black box testing. Testing functionality can be done from 2 perspectives: requirements-based or business process-based. Requirements-based testing uses a specification of the functional requirements for the system as the basis for designing tests. The requirements should be prioritized based on risk criteria, and use this to prioritize the tests. The techniques used for functional testing are often specification-based, but experience-based techniques can also be used. Test conditions and test cases are derived from the functionality of the component or system. A second target for testing is the testing of the quality characteristics, or non-functional attributes of the system, or component or integration group. Here we are interested in how well or how fast something is done. We are testing something that we need to measure on a scale of measurement, for example time to respond. Non-functional testing, as functional testing, is performed at all test levels. Non-functional testing includes, but is not limited to, performance testing, load testing, stress testing, usability testing, maintainability testing, reliability testing, and portability testing. The third target of testing is the structure of the system or component. If we are talking about the structure of a system, we may call it the system architecture. Structural testing is often referred to as white box or glass box because we are interested in what is happening inside the box. Structural testing is most often used as a way of measuring the thoroughness of testing through the coverage of a set of structural elements or coverage items. It can occur at any test level, although is it true to say that it tends to be mostly applied at component and integration, and generally is less likely at higher test levels, except for business process testing. At component integration level, it may be based on the architecture of the system, such as a calling hierarchy, a system integration, or acceptance testing. Test basis could be a business model or menu structure. At component level, and to a lesser extent at component integration testing, there is good tool support to measure code coverage. Coverage measurement tools assess the percentage of executable elements, e.g. statements, or decision outcomes that have been exercised, i.e. covered, by a test suite. If coverage is not 100%, then additional tests may need to be written and run to cover those parts that have not yet been exercised. The final target of testing is the testing of changes. This category is slightly different to the others, because if you have made a change to the software, you will have changed the way it functions, the way it performs, or both, and its structure. However, we are looking here at the specific types of tests relating to changes, even though they may include all of the other test types. The first of these types is confirmation testing, retesting. When a test fails, and we determine that the cause of the failure is a software defect, the defect is reported, and we can expect a new version of the software that has had the defect fixed. In this case, we will need to execute the test again to confirm that the defect has indeed been fixed. This is known as confirmation testing, also known as retesting. Like confirmation testing, regression testing involves executing test cases that have been executed before. The difference is that, for regression testing, the test cases probably passed the last time they were executed. Compare this with the test cases executed in confirmation testing. They failed the last time. More specifically, the purpose of regression testing is to verify that modifications in the software or the environment have not caused unintended adverse side effects, and that the system still meets its requirements. It is common for organizations to have what is usually called a regression test suite or regression test pack. This is a set of test cases that is specifically used for regression testing. They are designed to collectively exercise most functions, certainly the most important ones, in a system, but not test any one in detail. It is appropriate to have a regression test suite at every level of testing: component testing, integration testing, system testing, etc. The entire test cases in a regression test suite would be executed every time a new version of software is produced, and this makes them ideal candidates for automation.